So now we're going to take a closer look at our intervals and how we get our heights of our rectangles. And so I'm going to draw three of the same function. And in each case, we're going to go from A to B. Now, as we've already discussed, if n is the number of rectangles, then the distance b minus a divided by n is going to give us the width of each subinterval, right? We're going to break up the interval a to b into a bunch of subintervals like this. Now we're going to draw rectangles in three different ways. We're going to do it once with right endpoints. Once with left endpoints. And then once with midpoints. The basic idea, for example, with right endpoints, is to look at your first interval, and we're going to draw the height of our rectangle using the right endpoint of this first interval, meaning we're going to use this x value here, plug it into the function to get the height of this rectangle, like that. And so the height of that rectangle has been calculated using the right endpoint of this first little interval that I'm darkening in green. And then we go on to the second interval, right endpoint. We're going to get the height of our rectangle there, like that. And we continue with the next interval, right endpoint, like that. And then here, right endpoint. And then way over here, we're not going to get any rectangle at all, right? Because our right endpoint is on the x-axis. So these rectangles were put together using right endpoints. Well, let's think about this for a little bit. We want to find the x values of these right endpoints. And so we're going to have x equals, well, how do we start this? We start at A, and then we add over a delta x, right? That gives us our first right endpoint. And to get our second right endpoint, we're going to start at A, and then we're going to add 2 delta x's. And to get to the third one, we'll add 3 delta x's. So what does that look like? It's going to be A plus our delta x, which is b minus a over n, right? That's what we wrote off to the right there in black. And we want to add it once to get the first one, twice to get the second one. To get the third one, we're going to have 3 delta x. And so we're going to multiply this by the letter I, and we're going to let I count the numbers 1, 2, 3, going off all the way to, well, our nth rectangle. So again, the idea here is we are starting at A, and then we're adding delta x I times, right? There's once when I is 1, here's twice when I is 2, here we add delta x 3 times when I is 3, and then 4 times, et cetera, et cetera. From there, if we want to find the area of one of these rectangles, area, let's just say, of the ith rectangle, that's just referring to the 5th or the 6th or the 7th, right? Rectangle, just in general, the ith rectangle. that's going to be given by what? Well, we're going to evaluate the function at the right endpoints, right? We're doing right endpoints here, which is a plus b minus a times I over n, right? That's going to be f of that right endpoint. And then we're going to multiply that by the width, which is delta x. And so that's how we deal with finding areas of several rectangles. And when I say several, I mean n rectangles. It could be 5, it could be 10, it could be 100, it could be 1,000. We could let n go off to infinity. We've got our right endpoints, and we have our area of our rectangles using those right endpoints. Now, we could just as easily do this with left endpoints. So now we're going to look at left endpoints. And that's going to be a matter of looking at our first interval here and choosing the endpoint of that interval on the left, meaning I'm going to use this point here to get the height of my rectangle, like that, for my first rectangle. It's going to look something like this. Yeah, the height of that rectangle is based on the value of the function at that left endpoint. And then for the next one, we're going to get the height of our rectangle from this endpoint, right? The left endpoint on this second interval, which is going to put us there and give us a rectangle that looks like this. And then we do the same thing on the next one. We're using the left endpoint on the third interval, and we get a rectangle that looks like that, and another one like that, and one more like that. And so there we get areas of rectangles using left endpoints of each of our intervals. And so to get a left endpoint, we're going to start with x. Now, we're going to need I in each case, because I is counting the rectangles. That's what I does. You can see that in green right over here, right? It's counting our rectangles. So we're going to need I to count our rectangles. So I is going to go 1, 2, 3, 4, and so on and so forth. But again, we're going to start at A, but then we're going to add to that B minus A over N. That's it. That's delta X. But we don't want to just immediately add one of them and start there. We actually want to start right there. So when I is equal to 1, we want to add 0 delta x's, right? When we're talking about our first rectangle, when I is equal to 1, we're talking about our first rectangle. We want to stay here at A, meaning we don't want to add any delta x's to A. So what we do is we put I minus 1 here, because when you plug in 1 right there in for I, you're going to get 0 in that second set of parentheses. And so you're just going to start at A. But then when you put 2 in here for I, that's what's going to take you to this left endpoint here. Okay, that minus 1, when you if you compare green and purple, right? If you look here and compare this to this, that I minus 1 is having the effect of shifting everything to the left one interval, right? One subinterval, I should say. So there are our left endpoints. And so from there, just like we did in green, the area of the ith rectangle is f of these left endpoints, which gives us the height, times delta x. And just as we had in green, I is going 1, 2, 3, and then it's counting all the way up to n. And so there we have the story with left endpoints. And so looking at these two side by side, you'll notice that the green approximation of the area under the blue curve is going to be less than the actual area because we have all these gaps under the curve that are not part of those rectangles. And the purple, some of the areas of those rectangles is going to be more than the area under the curve because we have the little bits of those rectangles that are bleeding over, going above that blue curve. The thing about it is it doesn't ultimately matter because, as we've seen earlier, when we let the number of rectangles get really, really big, these little bits that are either sticking out above or these little empty spots below end up getting really, really small. Their areas approach zero, and so we're approaching the area under the curve. There's one more setup here, which I'm going to talk about briefly, and that's dealing with midpoints. And the idea is that we start at the midpoint of a subinterval like this, and we get the height of our rectangle from that value, like this. And then we do the same thing, midpoint of the next interval, and then we get the height of our rectangle there. So we have a little bit of each rectangle that's below the curve and a little bit that's above the curve. And same thing here. Pretend these are evenly spaced. I know it's not quite right, but good enough for our needs right now. Like that. So this is what it looks like when we use midpoints of each interval. And again, as we let the number of rectangles get huge, then we're going to find that some of the areas of those rectangles is going to get really close to the area under the curve. And so for midpoints, we start at A, and then we add on to that. Basically, we average, right? We take one of these, and we need to average these guys, right? We need to find the place in between, right? And then add that on, right, to A. And I won't go into a lot of specifics on it, but it looks like this: B minus A times I over N plus B minus A times I minus 1, I should say, I minus 1 over N, like that, times a half, right? We're averaging these. And from there, we can do a little bit of simplifying. I'm not gonna go into the particulars. We end up with B minus A times 2I minus 1 all over 2N. I equals 1, 2, 3, and going off to N. And of course, this is X equals that. So these are the midpoints. Okay, that's finding each one of these locations here on the X-axis. And so to get the area, we would then plug that into our function, right? We would put this in to our function to get the height of each rectangle. That's a B. And then multiply that by delta X, which is the width of each rectangle. So that's the area of ith rectangle. And you might be looking at this saying, well, the pink ones, right, the midpoints are the best approximation. And yeah, you have a point there if we're only going to do 6 or 20 rectangles. But again, with any one of these three, if we let the number of rectangles go to infinity, right, so many rectangles that we are dealing with a limit, all of these approach the same value, which is the area under the curve. Okay, and in more advanced calculus classes, you start looking at taking not right endpoints, not left endpoints, but some random point in here. Maybe it's not so random. I don't know. Maybe here you're getting a point there and getting the height of the rectangle there. And maybe in this one, you're using midpoint. Maybe here you're using a right endpoint. And we don't really do that in this class, but the concept is that no matter what point you choose in each interval, to get the height of your rectangle. When you take the limit as the number of rectangles goes to infinity, they're all approaching the same value, which is the area under the curve. Now, I mentioned midpoints very quickly. I'm not going to push those real hard in this class. I'd like us to understand right endpoints and left endpoints. And so that's what we're going to see in our next example. So example number 5, they want us to use 4 rectangles to find 2 approximations of the area of the region lying under the graph of f of x equals 6 minus x squared and the x-axis between 0 and 2. So we're going to do right endpoints and left endpoints with 4 rectangles, and that's going to give us our 2 approximations. So I'd like to first go ahead and sketch these, and then we'll start with right endpoints first. So first, let's figure out delta x. And you can see it from the graph that we have a distance of a half. But if we were to do it in general, right, we're talking about widths, right? That's our delta x right there. So we have delta x is equal to b minus a over n. Well, we have b is 2, a is 0, right? We're going from 0 to 2, right? Here's 0. And we have 4 rectangles, if I'm not mistaken, is what the plan is. And so that ends up being a half. So that is our delta x. And so that's going to be the width of each of our rectangles. And we're going to start off doing right endpoints. So we have x's doing what? Well, let's take a look. If we look at our first rectangle, the right endpoint of our first interval is going to be at a half. We bring that straight up to our function. And there is our first rectangle. Okay, so what did we do? We got at this x value by starting at 0 and adding delta x once. Okay, the next right endpoint is going to be here at 1. And how did we get that x value? We started at 0, I should say, and we added 1/2, which is delta x, times 2, right? We started at 0. If we add 2 times a half, we get to 1. The next right endpoint is going to be right here. And you might be seeing a pattern already. We're starting at 0. We're adding delta x, which is a half, 3 times. Then we go 1 more here. To get to that guy, we are starting at 0 and adding 1/2 4 times. And the numbers you see, 1, 2, 3, 4, right? These numbers in yellow are simply counting which rectangle we're on. So that's what our I is doing. I is going 1, 2, 3, 4. So we can write this in general. X is equal to, well, the 0 is not doing anything. So I'm just going to write 1/2 I, where I equals 1, 2, 3, 4. So hopefully that makes sense. If not, pause, rewind, rewatch that part, because that tends to be one of the trickiest things we have here. So we'll go ahead and use that. So we have the widths of the rectangles we know to be a half already. So now we need the height of each rectangle, right? Height of, we'll say, ith rectangle. That's going to be what? Well, let's think about this for a second. If we start with our first rectangle, right? We're trying to get this area right here. We want the height here at a half going up to the function, right? Well, what is that orange length? It's simply the value of the function at a half, right? It's going to be the height up to the function at a half. In other words, f of 1/2. So we can write that the height of our rectangles is going to be f of our right endpoints. Right? Same thing with this next one. We're getting the height for this rectangle that I'm coloring in now at 1. F of 1 is the height of that second rectangle. F of 3/2 is the height of the third one. F of 2 is the height of the last one. So in this case, that's going to be f of 1/2 I, our right endpoints. And so now we want to get the sum of the areas of our rectangles. So let's write that up. Sum of areas of rectangles. Well, we're going to add 4 rectangles, and they're all going to have the same form. So I'm going to have the height f of 1/2 I times the width, which is 1/2, right? This is height, that is width. We multiply those. When I equals 1, we'll have the area of the first rectangle. When I equals 2, we'll have the area of the second rectangle. When I is 3, we'll have the area of the third rectangle, and so on and so forth. And then we want to add them up. So we're going to put a sum I equals 1 to 4. So we need to simplify this into an expression that's easy for us to work with. So here we go. We're going to have the sum I equals 1 to 4. We are going to plug in 1/2 I right there into our function, right? That's how we get the height of each rectangle. In other words, we're going to take 6 minus x squared. Instead of x, we're going to plug in 1/2 I. So we're going to have 6 minus 1/2 I squared. Okay, this isn't any more complicated than taking an x value and plugging it into your function to get the height of that rectangle. And from there, we have to multiply by 1/2 because that's the width. So again, this is the height, this is the width of our ith rectangle, right? Of the ith rectangle. Then we can do it for I equals 1, I equals 2, and so on and so forth. So we're going to continue simplifying this. This is equal to the sum I equals 1 to 4. And we're going to get 6 minus 1/4 I squared, all of that times 1/2. That will become the sum I equals 1 to 4. Distributing the half, we get 3 minus 1/8 I squared, like that. Now I'm going to split it up into 2 summations. So we have the sum I equals 1 to 4 of 3 minus, I'm going to factor out the 1/8 and get the sum I equals 1 to 4 of I squared. And now we're going to get to use our formulas for summation. So you'll notice with the first summation here in yellow, we've got the sum of a constant. So we're going to use the yellow formula there. And the second one, we're taking the sum of the I squared. So we're going to use the green one. So let's see what that turns into. That's going to give us the constant 3 times the upper bound of summation, which is 4. So that's going to be 3 times 4 minus 1/8 times our upper bound of summation n, in this case is 4, right? The number of rectangles is 4. So we're going to take the green formula there in the upper right-hand corner of your screen, and we're going to put 4 in for every n. So we're going to have 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. Simplifying that, we have 12 minus We have a 1/8 here. We have times 4 times 5 times 9/6. We can cancel a little bit. Here we get a 3, here we get a 2. We can cancel here, we get a 4. So now we have 12 minus, what is that, 15/4, which is going to give us, well, it's going to give us exactly 8.25. So there is our first approximation using right endpoints. That 8.25 is the sum of the areas of those 4 green rectangles that you see, and that is an approximation of the area under the curve. Of course, it's less than the area under the curve because we have those white spaces there, right? These guys here, and this one, and this one, and this one, that we have these little gaps that are unaccounted for. But as we saw earlier, we're going to take care of those by taking a limit as the number of rectangles goes to infinity. So now let's go ahead and look at left endpoints. So what are the left endpoints going to look like? Well, let's go ahead and start here. If we look at our first subinterval, we're looking at the left endpoint, which is going to be right there on the y-axis, going up to there. We're getting the height of our rectangle like that. And so we do it again, getting the height of the next rectangle at 1/2. And the next one at 1. Then at 3/2. And there we have our rectangles we get from left endpoints. Okay, now let's think about how we're going to actually find these left endpoints. So we want left endpoints that are going to start right there. And we have to include I because I is counting our rectangles. So if we start with an x value of 0, right? And then we want to add the width, which is 1/2, 0 times. But we want this to be for our first rectangle, so we want I to be 1. So the way we can take I equaling 1 and change it to 0 is subtract 1, right? In other words, I minus 1, right? So actually, let's do this kind of like I did before. Watch. This first left endpoint is going to be x equals 0 plus 1/2 times 0, right? No delta x's, no widths. This one is going to be x equals 0 plus 1/2 times 1. And this one over here is going to be x equals 0 plus 1/2 times 2, and so on and so forth. We get to do it for 3 right there. That is 4 rectangles, right? So what are these? Well, this one right here in yellow is for our first rectangle. So if I represents our first rectangle, we put I minus 1, and the first rectangle would be 1 minus 1 equals 0. And this next one, we're going to put I minus 1, and we plug in 2 for our second rectangle, we get the 1 in yellow. For the next one, we put in 3 for I into this I minus 1, and that will give us a 2, and so on and so forth. So each one of these is an I minus 1, right? The fourth rectangle is what we have here, and we get it by taking 1/2 times 3, which is 1 less than 4. So the way we write that in general is we're going to have our left endpoints at x equals 0, right? That's starting at 0, and then add on to that 1/2 times I minus 1, where I equals 1, 2, 3, 4. And if you don't totally see that, that's okay. Pause the video and plug these in. Plug in 1 there. You're going to start at 0. Plug in 2 there. you're going to start, you're going to then have 1/2, you're going to have a half, and then plug in 3 and 4 and see what it does. It should give you each of these left endpoints that we've just written up here. Okay, so now we want to get the height of our ith rectangle. So height of ith rectangle is simply going to be f of the left endpoint, right? And that for us is going to be f of 1/2 I minus 1, or you can write I minus 1 over 2 like that. So that gives us the height of each of our rectangles. And so now we want the sum of the areas, right? So we want the sum of areas of rectangles I equals 1 to 4 of the height of the rectangle, f of I minus 1 over 2 times the width, which is 1/2. So from there, we're going to look back at our function way up here, and we're actually going to plug in I minus 1 over 2 to get the heights of each of our rectangles. And so that's going to look something like the sum I equals 1 to 4 of 6 minus I minus 1 over 2 squared, right? I took that I minus 1 over 2 and I plugged it up here into my function for x. And all of that is going to multiply 1/2. And so now we've just got to simplify this down and use our summation formulas to evaluate, and then we'll be in good shape. So what do we get? We have the sum I equals 1 to 4. We have 6 minus, well, if we square this, we're going to get I squared minus 2i plus 1 over 4. And all of that is being multiplied by 1/2. So here we have the sum I equals 1 to 4. If I distribute the 1/2, I'll have a 3 here minus I squared minus 2i plus 1 over 8. Like that. Let's go ahead and keep simplifying. We have the sum I equals 1 to 4. I'm going to split up this guy here into 3 separate fractions, distributing the negative sign. So watch carefully. We've got our 3. Let's write it like this. Let's write minus 1/8 I squared. Then distributing the negative, we're going to have positive 2 over 8 is 1/4 I. And then distributing the negative, we're going to have a minus 1 over 8 like that. Simplifying just a little bit further, I've got a 3 in front, which is the same as 24 over 8. And if we subtract 1 over 8, we're going to get 23 over 8. So let's go ahead and write the minus 1/8 I squared plus 1/4 I and plus 23 over 8, like that. So if we can go ahead and evaluate this, we're done. Well, there's good news, because if you look at what you see right here, and then we scroll up to an example we did earlier, right here, it's this, isn't it? That's exactly what we just came up with using left endpoints on our function with 4 rectangles. Great, we've done this work. We know what this is. The result of this thing is 10.25. So which example was that? That was example 3. So I'll just write down here equals 10.25 from example 3. And so what we have is we've just found in purple the sum of the areas of these rectangles here that are bleeding over our curve there. But the actual area under the curve is actually somewhere in between these two, right? What we have is the, I'll just say actual area under curve between 0 and 2 and above the x-axis is going to be greater than 8.25 because the green has all those gaps underneath the curve, but less than 10.25 because the purple has all those bits of rectangles that are going above the curve. And so we know our actual areas between those two. And again, as we've already talked about several times, as we have more and more rectangles, the areas of these sums of areas of rectangles are going to get closer and closer to the actual area under the curve. And what you see with more and more rectangles is this number gets bigger and bigger, approaching some number. This number gets smaller and smaller, approaching the same number. They're kind of squeezing in on the actual area under the curve. So what you'll notice is that we have what's called an upper sum and a lower sum. So this picture here represents a lower sum because it's a sum of areas of rectangles that's less than the actual area under the curve. And this one over here is what we call an upper sum, right? The sum of those areas are going to be more than the area under the curve. And so this next bit here in the notes is just kind of going through this concept of upper sums and lower sums and getting a kind of a generalized approach for using these approximations by rectangles. So we have this function f is continuous, and we're using n rectangles, just like we've discussed, over the interval AB. Then the width of the rectangle is, PDF conversion got rid of my delta and turned it into a capital D. So go ahead and make that a delta. Delta x. Here, I'll make the x dark too, so hopefully that's obvious what's going on. Delta x is b minus a over n, as we've already discussed. B minus a is the distance for the entire interval. We divide it into n parts, right? N subintervals, and that gives us the width of each one. Since f is continuous, we have the extreme value theorem, which says we have a maximum and a minimum on each one of those intervals. Okay, let me just quickly show you how we have that here. If we look at the second interval, this is the max on that second interval, and this is the min on that second interval. Okay, on every one of these subintervals, we always have a max and a min. Okay. And so this height here is going to be f of, using the notation I'm about to show you, capital M sub I, meaning this is capital M, the x sub I, the x value where we get the maximum. And this one's going to be little m sub I. So this height would be f of little m sub I. And the idea here is that because we have a minimum value and a maximum value on each interval, subinterval, we can get the lower sum by taking the minimum values on each of our subintervals times the width, right? This is again just height times width. And because we're using the minimum values on each of our subintervals, we're getting the lower sum. And over here, we're using our maximum value on the subinterval times the width, and that's giving us our upper sum. And so that's the idea with upper sum and lower sum. Now, as we mentioned in the previous example, if we take the limit Well, first of all, notice right here, we have a lower sum because we have little m sub I. And here we have an upper sum. But as we take the limit of these guys as n approaches infinity, it turns out that these two values are approaching the same thing, right? These two limits are equal to each other. And so therefore, and that is the area under the curve that we're trying to find. So this goes into a lot more detail in more advanced calculus classes, but that's the idea of what we're doing here to find the area under the curve. And we're going to go through and do that entire process with example 5. Example 5, find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis between 0 and 1. So if you pause for a moment and look back at the very first example in the section, these two problems go hand in hand, because in the first example, it said, go ahead and estimate the area under this same curve between 0 and 1 using, I think we used 4 rectangles. And then we looked at it on GeoGebra, right? So we're going to do the same thing here, but we're going to do it in general this time. We're not going to do it for 4 rectangles. We're going to do it for n rectangles. And we're going to take the limit. Well, let me back up. We're going to find the lower sum and the upper sum, and then we're going to take the limit as n goes to infinity, and we'll see that they approach the same value. And it sounds like a lot, but as you'll see, it's actually pretty reasonable considering the gravity of what we're doing, right? We're adding up areas of a number of rectangles that's approaching infinity. That's, again, pretty amazing. Anyway, so our graph of this function is pretty straightforward. It is parabolic, like that. And we're just going to imagine maybe, I don't know, I'm just going to put several intervals here and imagine a handful of rectangles like this, maybe doing something like that. This obviously looks like an upper sum, right? Because we're talking about the sums of areas of rectangles that are going above the curve. Pretend those are all evenly spaced. I know it's not great, but let's go ahead and find our upper sum first. And our upper sum is going to happen at, well, look at each one of these. It's going to happen at the right endpoint. So at right endpoints. And so you'll notice that sometimes an upper sum is going to be right endpoints, sometimes it's going to be left endpoints. It depends. It could be elsewhere as well, but it depends on the shape of the graph. So this graph is shaped differently from the previous ones, and that's why we end up with our upper sum being at right endpoints. And so we're going to have capital M sub I, that's the x value for the right endpoints, is simply going to be, I guess I should have found delta x first. Let's do that. Delta x is equal to b minus a over n, which in this case is 1 minus 0 over n, which is 1 over n. And to get the right endpoint, we're going to start at 0, right? We're starting here at 0, and we're adding a delta x, which is 1 over n, and we're adding it I times. So that means we have I equaling 1, 2, 3, all the way off to n. And so if we want to find our upper sum, which I'm going to use just the same notation as you see just above to the right there, I'm going to use capital S of n. It's a function of how many rectangles we have. We're going to have the sum I equals 1 to n. We want the height of the function at each of our capital M sub i's, right? Those are x values where we have our maximum, our tallest potential rectangle. And then we're multiplying that by delta x. And that's going to be the sum I equals 1 to n of our function is just squaring function, right? I'm looking over here. I just square my x values. So I'm going to take my capital M sub I, which is 1 over ni, and I'm going to plug it into the function. and multiply that by delta x, which is 1 over n. And so that's going to become I equals 1 to n. We're squaring, I'm just going to write it as I over n squared, right? That's using the function, squaring the x values to get the height of the rectangles times the width, which is 1 over n. This, of course, will simplify into the sum I equals 1 to n of I squared over n to the third, right? Because here I have n squared, and then I'm multiplying by another n, so I have n to the third. I'm going to factor out the 1 over n to the third, and now I have simply the summation I equals 1 to n of the I squareds. And of course, we have a formula for that in green to the right. And so I'm going to rewrite this as 1 over n to the third times the sum of the I squareds is going to be n times n plus 1 times 2n plus 1 all over 6. And so now we're going to simplify that. We're going to have, if I multiply the numerator out, right, the binomial, and then multiply in the n, I get 2n to the third plus 3n squared plus n all over 6n to the third. If you need to, pause the video and check that out for yourself, but it's right. And then I'm going to split it up into 3 fractions, right? I'm first going to look at this fraction here, and I'm going to get 1/3. Next, I'm going to look at this fraction here, and I'm going to get plus 1 over 2n. And finally, I'm going to look at this fraction here and get plus 1 over 6n squared. And so there is an expression that gives us the upper sum, meaning you can choose any n you want. You can do 10 rectangles, 20 rectangles, 50 rectangles, 100 rectangles, 1,000 rectangles. You can find the area, the sum of the areas of that many rectangles by simply plugging in the number of rectangles into this expression. It's a very powerful expression. Let's do it again for lower sums now. These are going to happen at the left endpoints. And I'll show you that in the picture in a moment. In other words, if we want the lower sum, I'll do it in some other color. We'll just go ahead and do, let's do this yellow. So here we have our first rectangle that has no height using the left endpoint. Then here we have our second rectangle using our left endpoint. Here we have our third rectangle, right? And the left endpoints are the smallest f of x value on that entire interval. And that's how we get our lower sum using the left endpoints, because the sum of these rectangles will be the lower sum. So where are those left endpoints? Well, using what we dealt with before, remember we need that I minus 1. So they're going to happen, call it little m sub I, at 0 plus, instead of I times 1 over n, we're going to get I minus 1 times 1 over n, which is going to look like that, where I equals 1, 2, 3, going off to n. And again, you can plug in 1 and you're going to see it's going to start at 0, and plug in 2 and it's going to give you 1 width, 1 delta x over, and so on and so forth. But let's go ahead and come up with our lower sum now, which is little s of n. Again, I'm using the notation you see at the top of your screen to the left, little s of n. That's going to equal the sum I equals 1 to n of f of little m sub I times delta x, which is the sum I equals 1 to n of plugging in I minus 1 over n times 1 over n like that, I equals 1 to n of, what do we have to do for our function? Again, look at the pink arrow up there. We got to square 1, or I minus 1, I should say, over n, like that. That's the function value, right? This is the height. We're evaluating each of our x values at f to get the heights of each of those yellowish rectangles, and then we're multiplying by the width in each case. And so we are actually in a really good place now, because if we look back, look at what we have here and compare that with example 4, look at what we have right there. That's exactly what we had in example 4, right? This I minus 1 over n quantity squared times 1 over n. That's great. We've done this already. And if you notice, we got this in pink, right? We got 1/3 minus 1 over 2n plus 1 over 6n squared. So that's what we're going to use from example 4. So we have that this is 1/3 minus 1 over 2n plus 1 over 6n squared. And again, we got that from example 4. And so we've done what they asked for. They wanted us to find the upper sum and the lower sum of the region bounded by our blue graph, our function f of x equals x squared, above the x-axis between 0 and 1. So here are our answers. But I want to take it one step further. We did this for n rectangles. Okay, well, what happens if we take the limit as the number of rectangles approaches infinity of our little s of n, which is the limit as n goes to infinity, the number of rectangles goes to infinity of 1/3 minus 1 over 2n plus 1 over 6n squared. But we know how to do that. If we let n get huge here and n get huge there, those two terms are going to go to 0. That's a pretty straightforward limit. It equals 1/3. And if we do the same thing for capital S of n, the limit as n approaches infinity of 1/3 plus 1 over 2n plus 1 over 6n squared, guess what? We get the exact same thing. And so what we found here is the true area under the curve. True area under the curve. When I first saw this, when I took this class, I thought that this was mind-blowing for me. I was completely floored by this. The fact that we're able to come up with an expression to be able to add up as many rectangles as we want, millions of them, hundreds of millions, billions of these rectangles, and we always will get these areas approaching the same value, whether it's the lower sum or the upper sum, they're approaching the same value, and that's the area under the curve. Pretty astounding stuff. So what we've come to is kind of a generalized statement of this, which is basically saying that if you notice right here, you've got height, you've got width. Okay, the one weird thing that they've done here that we haven't talked about is this x sub I star. And all that's referring to is in a subinterval, you can use any x value in that subinterval. You can use a right endpoint or a left endpoint or a midpoint or any other point in that subinterval. That's what x sub I star is referring to. So here we have f has to be a continuous function. It's non-negative. So, right, we have some kind of function like this. It's non-negative between a and b. And if we go ahead and think about our rectangles, right? We can draw a bunch of them like this. We can take midpoints if we want. We can take right endpoints. We can take left endpoints. It doesn't matter. Either way, we can do mixtures of these things, but in each interval, we take a certain x sub I, any one of those in there, put it into the function to get the height, multiply by delta x. This whole quantity here is an area of a rectangle, of each rectangle. We add them up from 1 to n, and then we take the limit as n goes to infinity. And we end up with the area under the curve. And again, I've got a PDF conversion issue. This capital D should be a delta for delta x. So that's how we're finding area under curvy regions. Now, as we proceed into chapter 5, we're going to start coming up with more efficient ways of doing this. And we're going to connect it with antiderivatives that we did in section 4.9. But that's the idea. And feel free to go on to Canvas and play with the GeoGebra app that I created for this. And you can put in different functions. You can change the number of rectangles. You can change A and B and kind of get a sense of that.